Good morning, everybody. So first up today, let's talk about the exam for Friday. So I have some instructions on the course website. Let's just review those for a minute. Try again. Okay, so here on the course website, we have the study guides. So you can click on that. Study guide for exam 3. And this has some instructions about what we're doing for the exam. So at 8 o'clock on Friday, I will post the exam on the remote exam downloads tab of the course website. And I would like for you to print out, download the exam, print it out, complete it, scan it back to a PDF format, and upload it to Gradescope by 5 p.m. Boston time Saturday. So you have more than a day to do this exam. So that should take care of you who are in other time zones, and that should take care of people who have extra time. If you don't have a scanner, you can use if you don't have a scanner, you can use your cell phone to convert the pages to PDF, and there are instructions for doing that here. Maybe many of you have already done something like this for other courses and maybe for the lab, so you should be technologically competent to do that. If you can't print out the exam, just get a blank sheet of paper and try as closely as possible to mimic the page numbering and also the spacing and the location of the exams. It doesn't have to be perfect, but if you can't print out the exam, just take the exam on a blank sheets of paper, but lay out your answers in a way that closely resembles the exam, as close as you get, as close as you can. It's important that we work together, right? And it's important that you submit a PDF to Gradescope, not a cell phone picture, not any kind of file type that is other than PDF, not a Microsoft Word document or anything of that nature. Please, let's work together so that please try to submit a PDF. Okay. If for some reason the Gradescope will not accept your exam, email me the exam, and I'll try to take care of it that way. But what you're emailing to me is a PDF document, please. The exam is closed book and closed notes. I'm giving you over a day to do this exam. You are not to confer with classmates or friends or try to look up stuff on the internet. I am testing your integrity. If you are dishonest in small things, you are going to be dishonest in big things, right? And so if you feel that you have to cheat on an exam in college, when you get into the work world, you are going to be a dishonest person there. If you are dishonest in small things, you are dishonest in big things, right? Like patient care, handling of money, personal relationships. It's just a pattern. So I'm trusting you and I'm hoping that you will observe the highest standards of academic integrity. Okay. So fiddling around. Oh, that's wrong. Where's my video? Here you are. Any questions about the exam setup? Any questions about the exam setup? Okay, so if there are no questions, then if you think of something to ask me, either unmute yourself or send me an email and try to deal with it that way. All right, so what I'm going to
I
talk
have a question.
is not going to be on the exam, but a lot of these the topics that we're going to talk about today are have points in common with what is going to be on the exam, and that's going to be writing mechanisms, product prediction, and also recognition of patterns. Okay, the subject of today's lecture is the imine. If you're lucky enough to take biochemistry, biochemists call imines shift bases. So maybe when you get to biochemistry, the professor there will be talking about a shift base, but an organic chemist calls these compounds imines. All right, so first of all, when we're studying these reactions, one of the things that you're studying, a very important thing that you're studying, is recognition of starting materials, reaction conditions, and products. You can't write the mechanism of the reaction every single time you're trying to predict a product. You're just never going to finish writing the mechanism in time. So you have to recognize the starting materials, the reaction conditions, and the products. In other words, who lives to the left of the arrow, who lives above the arrow, and who lives to the right of the arrow. And what I like to call the recipe. Okay, so the recipe for the imine is an aldehyde or a ketone. This is just a generic representation of an aldehyde or a ketone plus a primary amine. And remember way back when we were talking about the nomenclature, we talked about what a primary amine was. So let's just refresh that. A primary amine, you're looking for NH2. That's what defines a primary amine. But nitrogen forms 3 bonds, so that the primary amine is always going to have NH2, but that nitrogen atom is going to be bonded to a third thing, which I'm calling Z. And Z here can be lots of things. Z could be another hydrogen atom, in which case our quote-unquote primary amine is the inorganic compound ammonia. Z could also be an organic group, such as a methyl group, right? Nitrogen forms 3 bonds. You're looking for a primary amine. A primary amine means NH2, but nitrogen is going to form a third bond to something else. That something else could be a methyl group, or it could be a benzene ring. Sure, why not? Or it could even be an OH group, or it could even be another NH2 group. It can be lots of things. That's not the business end of the molecule. The business end of the molecule is this NH2. Okay, so those are the starting materials, right? These are the reactants. The imine formation is reversible. So I'm going to put those reversibility arrows. And the imine, although it can form under acidic conditions, basic conditions, and neutral conditions, we only have time to talk about imine formation under acidic conditions. Oh, this chalk. And so that means you're going to see an H plus above the arrow, acidic conditions. Okay, so that's who lives to the left of the arrow, that's who lives above the arrow. What about the products of the reaction? Okay, so the carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. The carbonyl oxygen of the aldehyde or ketone, that's gone, and the two hydrogens that the nitrogen came into town with in that primary amine, they're gone. So the carbonyl oxygen and these two hydrogens pop out as a molecule of water. And so we've seen that before, right? So water is also the byproduct of an acetal formation. And this third group, this Z, whatever it is, and it can be many things, that remains on the imine nitrogen. So this is the imine. The carbon-oxygen double bond is replaced by a carbon-nitrogen double bond, and the two protons of the primary amine are gone, as is the carbonyl oxygen of the aldehyde or ketone. They pop out as a molecule of water. Okay, so we don't need to talk about mechanism to predict products. So let's just try to get comfortable with this reaction and predict some products. Okay, so what is going to happen here when we have this acetophenone and react that with ammonia? Acid catalysis, draw the structure of the product. So you're just recognizing this pattern. You see, I've given you the recipe for the imine, so draw the structure of the product. The carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. The primary amine loses its two protons, but that nitrogen atom forms three bonds, so whatever that third thing is that's not a proton remains. Okay, so the product imine here is going to be the carbon-oxygen double bond is gone. It is replaced by a carbon-nitrogen double bond. And remember this ammonia here, this could be written NH2H. It's not, for us, it's a primary amine. This is the inorganic compound ammonia. It's not really an amine, but for us, it is we treat it as if it were a primary amine. Okay, so how did that go? All right, so let's try some more. All right, so let's try this product prediction. What's going to happen here? The carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. And the other product of this reaction is water. Okay, so let's try a few more. just product prediction. Okay, what's going to happen here? Predict the product here. Is it the recipe for the imine? Oh my heavens, yes. I see a primary amine, NH2. I see an aldehyde or a ketone. But this will be an example of an intramolecular imine formation. We saw these kinds of reactions when we were talking about hemiacetals and acetals. If a 5-membered ring or a 6-membered ring can form, it will do so because those are thermodynamically stable systems. So the carbon-oxygen double bond is gone. It's replaced by a carbon-nitrogen double bond. The 2 protons of the primary amine, they're gone, as is the carbonyl oxygen. But now when I hook up this primary amine nitrogen to this carbonyl carbon, right, this carbon right here, I'm going to put a little dot on him, is this one. I see that the dot is tethered to the nitrogen in such a way that a 1, 2, 3, 4, 5-membered ring can form. And so that is thermodynamically stable. CH2, 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 and then nitrogen. CH2, 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 and then nitrogen. So that's intramolecular imine formation. So the imines form by an intramolecular reaction. If a 5 or a 6 ring can form. Right, nothing new. We've seen this before with the acetal and the hemiacetal. Okay. Now, let's pick up another theme that we saw with hemiacetals and acetals, and that is the reversibility of imine formation. We know that hemiacetals and acetals form reversibly, so do imines. So let's try some product prediction problems based on reversibility of imine formation. Okay, so imine formation is reversible. So what we mean by that is if we start with an aldehyde or ketone and a primary amine and add acid, right? I'm not drawing an equilibrium arrow because I'm just thinking about the forward reaction right now. If we start with an aldehyde or a ketone and a primary amine and add acid, what we're going to get is an imine and water. But imine formation is reversible, meaning if we start with an imine and add water and add acid, the imine is going to fall apart. This is exactly the same thing that we saw with a hemiacetal and an acetal. The imine is going to fall apart. The imine nitrogen reverts to a primary amine nitrogen. The imine carbon, I'm going to put a little dot on him, reverts to a carbonyl carbon. of an aldehyde or a ketone. So this is what we mean by imines are formed reversibly. So it's just this master equation here, but we have to realize that it can happen in the forward direction, in the back, and in the reverse direction. How will you know the difference? The recipes are different. Here's the recipe for imine formation in the forward direction. Here's the recipe for reversal of the imine formation. Right? We have different things living to the left of the arrow, to the right of the arrow, although both reactions are catalyzed by acid. Okay, so let's try with a couple of those. Okay, so what if we have, let's say, all right, so what would be the product here? Oh, this is the recipe for reversal of the formation of the imine. I see an imine. What's that? It has that carbon-nitrogen double bond. And I see water and I see acid. So the imine nitrogen reverts to a primary amine nitrogen. And the imine carbon, this guy, reverts to a carbonyl carbon. So a hideously ugly drawing, but it makes the point. That would be the structure of the product, where that carbon-nitrogen double bond of the imine has been destroyed and it has gone back to being primary amine and carbonyl carbon of an aldehyde or ketone. Okay, so let's try one more. And then we can talk about mechanism. Excess water and acid, what will be the structure of the products here? So draw the structure of the product. So there's the imine, the carbon-nitrogen double bond. There's another imine, carbon-nitrogen double bond. We're told that we have enough water to take care of both of imines, and so we're going to get reversal there and reversal there. So the products here will be the imine nitrogens fall off as primary amine nitrogens, and the imine carbons, these guys here, putting a dot on them, they revert to carbonyl carbons. So the products of this reaction would be this benzene 1,2-diamine and cyclohexane 1,2-diol. Okay. All right, now let's talk about mechanism of imine formation. And again, we see a lot of points of commonality between the mechanism of the imine formation and the mechanism of the formation of a hemiacetal and of an acetal. So let's keep everything nice and general here. There's our aldehyde or ketone. There's our primary amine. We're going to add acid. We're we're going to get an imine plus water, and now we're going to write the mechanism. All right, so one of the things that we've said, I think maybe probably even more than once, is that whenever you see a carbonyl compound sitting around under acidic conditions, what are the first two things that nearly always happen mechanistically? First thing, protonate the carbonyl oxygen. Second, attack the carbonyl carbon with a nucleophile. Okay, I see I made a little mistake here. I forgot to put in my Z. So this should be like that. Okay, protonate the first step of the mechanism. Protonate the carbonyl oxygen. Protonate the carbonyl oxygen and then attack the carbonyl carbon with the nucleophile. The nucleophile in this imine reaction is the nitrogen atom, which has this unshared pair of electrons on it. So the nitrogen attacks the carbonyl carbon. Oxygen gobbles up that electron pair. We've seen this step bazillion times. Step like this a bazillion times. So we have an intermediate that looks like this. Okay, and so notice that those two protons, they're still there in this intermediate, and notice my handling of the charges. Way back, first lecture of the year, when nitrogen forms 4 bonds, it must have a positive charge. Okay, now there's a lot of fiddling and diddling with protons. Nitrogen's pretty electronegative. It doesn't like to have this positive charge. It wants to get rid of it. And as we've seen frequently, one of the ways these electronegative atoms rid themselves of a positive charge is by undergoing a deprotonation. So this nitrogen atom, something in solution, comes along. It could be water, it could be some other base, comes along and removes that proton from the nitrogen. And this happens so that the nitrogen atom can be neutral. And now we have this proton swimming around in the reaction mixture. But we have a lot of protons in the reaction mixture, right? Because we added acid at the beginning. This reaction is happening under acidic conditions. So one of those protons in the solution comes back on this molecule, but it's not going to come back on this nitrogen this time. It's going to come back on this oxygen. So the next step here is going to be the reprotonation of this hemiaminal, which is what that's called. Not important. It's called. It's going to be this protonation on oxygen. Okay, so down here we have this intermediate here where that oxygen atom has picked up that proton and has now become positively charged because oxygen, when it forms 3 bonds, as it's forming here, has to have a positive charge on it. And again, oxygen is electronegative. It doesn't like to have that positive charge. It's going to rid itself of that positive charge by heating up the electron pair in this bond, holding it to this carbon atom. So that explains the formation of water. And what's left behind is a carbocation intermediate, right? And we've seen stuff like this plenty of times when we were talking about acetals. And now This nitrogen atom here undergoes a deprotonation. A base comes along and removes this proton, and these two electrons here, electrons are negative, these two electrons here rush up here to satisfy and to quench this positive charge. So we get deprotonation. Deprotonation, the electrons rush up there to satisfy that positive charge. Remember this carbocation here, he only has a sextet of valence electrons. And that new double bond is our new carbon-nitrogen bond in the imine. Okay, so that's the mechanism for the formation of the imine. And we see a lot of steps in this mechanism that are in common with the steps of the formation of the hemiacetal and the acetal. Now, how about let's talk about the mechanism for the reversal of the formation of the imine. Okay, so what is going to happen here is we start with an imine, add water, add acid. The imine carbon goes back to a carbonyl carbon, and the imine nitrogen reverts to a primary amine nitrogen. So let's write mechanism for the formation here. Okay, and so this mechanism is, it has points of contact with our hemiacetal and our acetal mechanisms, but now we're dealing with nitrogen instead of oxygen. If you saw a carbon-oxygen double bond sitting around in acid, what would you do first mechanistically? Protonate the carbonyl oxygen. Then what? Attack the carbonyl carbon with a nucleophile. Right, this isn't a carbon-oxygen double bond, it's a carbon-nitrogen double bond, but it behaves in a very similar manner. So our first step is going to be protonation of the imine nitrogen. Right, if this were a carbonyl oxygen, this is the first thing that we would do. So this is an analogous process. Protonation of the imine nitrogen. And again, I'm putting a positive charge on that nitrogen because nitrogen has a positive charge when it has 4 bonds. Then what do? We attack the carbonyl, we attack the imine carbon with the nucleophile. And what's the nucleophile? Water. Water has this electron-rich oxygen atom. So the oxygen comes in and it attacks the imine carbon. We can't stop there because if we stop there, we're going to have a carbon with 5 bonds. So we have to chase away one of these bonds in the carbon-nitrogen double bond, and those electrons go onto that nitrogen. Okay, so we have an intermediate that looks like this. Okay, now, just like in the acetal mechanism, just like in the imine mechanism, fiddling and diddling with protons. So this oxygen atom is going to lose a proton. That proton is going to go off into the solution. It's never going to be heard from again. But we have a lot of protons in the solution. One of them is going to pop on this nitrogen atom. So we have, instead of writing all of those steps I'm going to introduce this notation, plus minus H plus. That means take away a proton, minus H, add a proton, but somewhere else in the molecule, right? This is just a time-saving way of representing all of this fiddling and diddling with protons. Proton on oxygen is going to go away into the solution, never heard from again, but you have a lot of protons in the solution. One of them is going to pop back on this nitrogen. So that brings us to this intermediate now. And again, nitrogen doesn't like to be positively charged. Neither does oxygen. It's highly electronegative, so it doesn't want to have that positive charge. It's going to gobble up this electron pair. And there is our primary amine. And the other product of this step is going to be a species that looks like this, a carbocation. There, now the last step is going to be the deprotonation of this oxygen, and these electrons are going to rush in here to satisfy that positive charge. We saw that in the forward imine reaction. So this electron pair goes away, it forms that new double bond there, H plus comes out, and there is our aldehyde or ketone. All right, so these are the steps of the mechanism of the reversal of the imine. And if you study this, and if you look at the mechanism in the forward direction, you see it's all of the same intermediates. It's all of the same intermediates, except now it's like you're playing this movie in reverse. Okay, so let's take a little short break here, and maybe let's show you some pretty pictures about imines. Let's see. If I can. Where am I? Okay, just diddling here with the screen. What happened to my screen share? Oh, Lord. Okay, just hold on here. If I can get this in a reasonable amount of time, I'll just talk about it. Uh, okay, never mind. Man, this thing is so complicated. Oh, thank you, Jesus. That didn't do anything. Forget it. Okay. So instead of showing you pretty pictures, how about let's talk about some of the uh, talk about some of the applications of the immune. You know, I know very little about diabetes because I don't have diabetes and no one in my family does. It's not a part of my world, but I know it's a very important condition that restrains a lot of people in a lot of ways. One of the ways, it's kind of an old fashioned way, but one of the ways that you can monitor your blood sugar level is by this immune reaction. Way back before we had wearable glucose monitors and the finger pricking and all of that other stuff, the way that people would monitor the level of glucose in their blood would be by urinating into a cup and then dipping in a test strip into that cup. And if there was sugar, if there was glucose in the urine, it would react with a compound on the test strip and it would produce a blue color. So I want to talk about this reaction because this brings together our talk about the imine and the chemistry of the carbohydrates. So the most important sugar, the only sugar that you can derive metabolic energy from, is glucose, right? And this is the sugar that you're trying to detect in urine if you're diabetic. And so glucose, just like every time we talk about carbohydrates, there's all kinds of writing and all kinds of dashing and pledging. So what I've represented here is the beta D glucose, right? So this is the most common form of glucose that is found in solution, and one of those solutions would be your blood, which is essentially an aqueous solution. So this is beta D glucose, and we know that it's a hemiacetal, and hemiacetals are in equilibrium with their carbonyl parent, so that glucose, there's a small amount of the carbonyl version, the open chain version of glucose, where this hemiacetal carbon is in equilibrium with a carbonyl carbon, right? And that's the open chain form of glucose. That's an aldehyde. And in these test strips that pretty much only very skilled clinicians use these anymore, But if you're going to a hospital, they're likely to test your blood using, or they could test your blood using these test strips, because those test strips give a lot more information than just how much glucose you have. The test strip is impregnated with this compound. And so we see this has set up a reaction between an aldehyde and a primary amine. So the product of this reaction is going to be an imine, where the carbon-oxygen double bond of the glucose is replaced by a carbon-oxygen double bond, carbon-nitrogen double bond of the imine. And so we have this adduct here, and this thing is blue-green. So, and how dark the blue-green color is, that is telling us how much glucose it is. So this is a practical application of the imine. Okay, now I want to get into the reactions of the imine. Now we know how to make them. We know how to tear them apart. Let's spend a few minutes talking about some of the reactions of the imine. Two important reactions. We only have time to talk about one of them today. We'll finish talking about it at the lecture after the exam. I'm not planning on having a lecture on Friday, the day that you're supposed to be taking the exam. I'm not planning to have a lecture then. So we'll continue talking about the reactions of the imine after the lecture. Okay, first up, reductive amination. All right, so this is one of the important reactions of an imine. And just like every reaction that we cover, it has a recipe. And so the recipe here for this reductive amination is you start off with an aldehyde or a ketone and a primary amine. It's acidic conditions. You're going to get an imine and water. Right, so we went all through that, how that imine forms. So you get this imine. So that would be step one of reductive amination. And now in the second step, in a totally separate step, we take this imine and react that with hydrogen in the presence of a metal catalyst. So this is step one of reductive amination. Step two of reductive amination, we take the imine that we formed in step one and react that with hydrogen in the presence of a metal catalyst. And so the metal catalyst would be written underneath the arrow, and we have a lot of options, and we'll see that this reaction has very expensive tastes. We could use platinum. And anyone out there into jewelry? Anyone out there like to wear jewelry? You know, silver is expensive. You know, gold is expensive. Platinum is even more expensive. So we could use a platinum catalyst, or we could use a palladium catalyst, PD. That's just another element there on the periodic table. And this stuff is even more expensive than platinum. So this reaction has very expensive tastes. So what is going to happen here in reductive amination is this carbon-nitrogen double bond of the imine will be degraded to a single bond, and the elements of hydrogen will add across where that double bond used to be. So we get hydrogen at one end of where the double bond used to be, and the second hydrogen on the other end of where the double bond used to be. And so this is a way, the reason that this anyone would care about this reaction is that this is a way of making a new and bigger amine from a pre-existing and less complicated amine. Okay, so let's leave this up here and let's try some product prediction about reductive amination. So let's say if we start with this aldehyde, and then in step 1, react that with methylamine and acid. So this is our step 1 of our reductive amination. This is the recipe for the imine. The carbon oxygen double bond is replaced by a carbon nitrogen double bond. There's the imine. And now in our second step, we take this imine and react that with hydrogen. I'm going to draw the product up here. We react that with hydrogen over a platinum or palladium catalyst. In this example, I'm using platinum, but I could use palladium. What is going to happen is that the elements of hydrogen are going to add across where the double bond used to be. And so we get, there used to be 1 hydrogen there. There are now 2. Where did that second hydrogen come from? From this H2. This nitrogen also picks up a hydrogen. And so we see here the elements of hydrogen have added across where the double bond used to be. And the overall importance of this reaction is we've made a complicated, bigger amine from a less complicated, pre-existing, smaller amine and an aldehyde or a ketone. Okay, so after the exam, we'll talk about the mechanism of this reaction and more examples. But I wonder, any questions about anything that we can deal with now before we sign off? Any questions about anything before we sign off for today? So I guess not. Well, I do. Okay, go ahead.
Question. Yeah, if I'm unable to upload it, I was able to upload the homework as a PDF, but I took pictures of the papers and then copy pasted the pictures in a PDF file and then upload it. Is that fine as well? It looks like a PDF, like it's a PDF,
Yeah,
but I just took pictures instead of scanning.
That's fine. I want, please do not send me a cell phone picture, right? It has to be a PDF. The file has to say .pdf, please, not JPEG or bitmap or PNG or anything like that.
Yeah, you can't upload anything else on Gradescope. So I uploaded a PDF only that I just took pictures of it rather than scanning. Okay, thank you.
But can you upload it in the correct order? Page 1, then page 2, then page 3, and so on, not just a random?
Yeah, that's what I try to do. Maybe it switched them.
Yeah, don't switch. Gotta work together.
Okay, thank you.
Anybody else have any questions about anything? Well, if you think of something, email me, and if you can't upload and download the test, email me and I'll try to fix it for you. Anything else? Okay, well, I guess we'll sign off now and we'll see you down the road. Oh, okay.